Okay, so let's go ahead and pick up pretty much where we left off. There's a couple of quick things I want to talk about on this problem. There still seems to be a little bit of misunderstanding about the delta n. So when we're converting between Kc and Kp, we have this delta n here. And where that comes from, if you go back to the derivation that we did, that actually comes from a rule of exponents, and that's coming from products minus reactants. Now this is not the number of moles in the reaction. It's not like the number of moles if you're talking about concentration or something of that sort. It's the number of moles based on the stoichiometric coefficients. So as if this is a 1, and a 1, how many moles do we have on the product side? And how many on the reactant side? And what is 2 minus 1? Good. So that's where that delta n is coming from. And then one more quick thing. I just had the wrong number of sig figs, so I've added in a 4 here to give it 3 sig figs. So that's a tiny little change. You probably will not, do significantly worse in this class if you're relatively careful with sig figs. If you get a tiny one wrong here or there, it's not going to murder your grade. It's not that big of a deal. It's actually really, really important in lab, both in terms of real life experiments and knowing how accurate you're being, and in terms of your actual lab class that you're taking. Because it is important, they're pretty picky about it. So if you have issues with sig figs, come let me know and I can walk you through it again, since I know sometimes it gets forgotten about since Chem 1A. Okay, continuing to move on then. So the next question is, when is Kc equal to Kp? And we can go about trying to answer this a few different ways, but let's actually do it by looking at the equation. We can play around with some more math and some more equations for a little bit. So I'm going to start there. Now, if we want Kc and Kp to be equal to each other, what does that mean that this whole thing has to equal? That whole thing has to equal 1, right? Because if this all equals 1, then Kc is going to equal to Kp. Well, is there anything that we can do to R to make it equal so that that makes it all equal to 1? No. What about temperature? No. But what happens if that is equal to something? What does that have to be equal to make the whole thing go to 1? Exactly. So if delta n equals 0, well, then Kc is equal to Kp. Okay. So we have this when this number equals 0. Well, what does that really mean? If we change that delta n and we put it into words, what is that actually saying? There's no change in moles. The number of moles in the reactant side is the same as the number of moles on the product side. So that's a nice thing to keep in mind. Because if you look at an equation and you say, actually, let's put in one more word here to be really specific. Is it just number of moles? Number of moles of what? What phase are we talking about? Yeah, so let's do this. Gaseous products and gaseous reactions. Just to be extra specific. So if your number of moles of gas on both sides are the same, then your Kc and your Kp are going to be equal to each other. And that can be a handy trick for saving you a little bit of time. Okay, so let's do a little bit of review on what we did last time, just that last little section. So remember, we can use K to tell us whether the reactants or products are favored. So if K is a lot greater than 1, that means that our numerator is going to be much higher, which means that our products are favored, because it's products over reactants. And remember that this little section is true for all the K's. So when we start going on in next chapter and the next chapter and I talk about it, you'll know it before I even say it. Now if K is a lot lower than 1, That means that which is bigger, your numerator or your denominator? It's less than 1. Denominator, right? Okay, since it's products over reactants, that means that your reactants are favored. If it's about 1, then they're about equal. Then you have about the same amount of products and reactants. Okay? Only our gas and aqueous species are included in our equilibrium constant expressions, and we're going to talk about that a little bit more in a minute, but for right now we just know that that's true. And concentrations at equilibrium vary depending on your initial conditions, and so we use K instead of just using the ratios, right? If you go through and you look at that big long table I gave you, thank you so much. If you look at that big long table I gave you, and you try to just fill in ratios, it's not going to work out. But once you raise them to the exponents, now every single time, regardless of your initial conditions, you end up with the same number. Okay. Now that we've finished that up, and I've given everybody a little bit of chance to show up a couple minutes late if needed, quick announcements again. I know I talked about this last time. A lot of this is actually just all of it's repeat, but just in case because of enrollment issues, make sure that this week you go online, you read the syllabus. I very briefly covered the most important topics, but there's a lot of information in there. Make sure you download the PowerPoint slides if you need it. Very shortly, 17 and 18 should be up. I'm just kind of finalizing things up a little bit. I also put the form that I have on the document camera, these pages, I put the blank versions of those up for you too if you want them, so that I know some people like actually writing in the same format I do. So if you want them, they're up now too. Make sure you register for Mastering in Chemistry. Be really careful. There's 2 really important things here. You have to register with your UCI email address. This is to prevent duplicate accounts. So if you don't do that, we kick you out and you don't get a grade for the homework, which can be a little detrimental. And make sure that your ID number is correctly. If your ID number isn't entered correctly, you don't get a grade for your homework at the end. So nothing really happens except at the end your grade doesn't get recorded, which is obviously a problem. So make sure you do those 2 things. Go ahead and get your extra credit for chapter 16 done. I moved it out a day so you have an extra day on it. Normally those will always be on the other day, but I gave you an extra day because class just started. And then just complete this. It's not due till Monday. It's fast, it's quick, it's easy. Get it done and over with. And then don't forget, if you're someone who likes to ask a lot of questions and have it right available and you're using your computer anyways, Allison's available on the chat room to kind of help out here and there if you have quick questions that you don't really want to ask in class, but maybe you want answered or you're curious about, whatever. And then weekly surveys, don't forget to fill those out. You should also just come to office hours and talk to me in person so I can help you out too. Come up after class and talk to me in person so you can help it out. But if you're someone who just can't handle talking to a person in person, I know I'm super scary looking, so you can throw them up there too. Especially if you just have a big topic that you're confused on and maybe think that a lot of people are. I can use that to kind of do some review for you guys if you need it too. It gives me a little bit of feedback. Okay, next section. So this is kind of 2 quick clarifications, review. There are 2 things that I've mentioned and we've talked about, and I kind of breezed through them and didn't really explain why, because at the time I just wanted us to be able to use it. So now let's talk a little bit more about why. So the first one, why is only gas and aqueous species included in the equilibrium constant? Now, there's a couple of different ways of thinking about this. From a math standpoint, what we say is that their activities are equal to 1. Now, that doesn't mean a huge amount. So let's think about it a little bit more conceptually. When we have this solid sitting in the bottom, it doesn't matter if we have a lot of solid or if we have a little bit of solid, their densities are still the same, right? You're not going to, because you have more solid, have a denser packed solid. So their concentration never changes. And we don't even really think of it in terms of concentration, right, if it's a solid. And the same thing is true for liquid, it just solids make a better picture. And so we don't include this. We say, okay, this doesn't matter because it's not changing. If something isn't changing at all and it's not affecting the amount of products and it's not affecting the amount of reactants, it's not doing anything to the equilibrium constant. So it effectively does get filled in sort of a magic way that we don't talk about. It gets filled in as a 1. And so it doesn't matter at all, okay? So that's what's going on there. Both of these are really more sort of curiosity / more explaining type things for you. And then the last one is K in units. And this goes a little bit more into what I meant when I said activities. This is not something I will test you on, by the way. It's just so that you understand why we're not using units and it doesn't seem arbitrary. We do actually use units. It's just that when we fill in concentration, because you may be looking at this and saying, look, I'm filling in a bunch of concentrations to this equation. Sometimes all of them cancel and sometimes they don't. Why wouldn't my units change? Like, remember when we did the kinetic K, and by we I mean you guys, did the kinetic K in 1B, our K's changed around, right? That kinetic K, a whole different kind of K, had those units that changed based on the exponent. This doesn't do that, and that's just because of the definitions and how they decided to fill them in. We're always filling them in over a particular unit. So we're actually filling in a pressure over 1 atmosphere, or a concentration over 1 mole per liter. And when we do that, it cancels the units. So every single time you fill in a pressure, it actually is a unitless thing because you're filling it in as 1 over atmospheres. And every time you fill in a concentration, you actually are filling in something that's unitless because when you fill it in, you're going to be filling it in over this concentration naught, or 1 mole per liter. So that's kind of going on behind the scenes. Notice we didn't need that to be able to do the problems. I did the problems first and we did just fine and we just said they're unitless and moving on. But this is the reason for it. So this is why we can just effectively ignore it. You're not allowed to just ignore things in chemistry unless you have a reason. This is the reason. Okay? So the short version of both of those, only aqueous and gas. You do not include solids or liquids. Now, what's the difference between a liquid and aqueous? This got asked last time and kind of got brought up again in office hours a bunch. Aqueous is water with things inside of it, right? So if you have sodium chloride, salt, dissolved in water, that sodium chloride is aqueous. The water isn't aqueous, the water is water, it's a liquid. The sodium chloride dissolved in water is aqueous. So that's your difference. And then your K doesn't have units. And this is true for all of your equilibrium constants. It's true for your Ka, your Kb, your Ksp, all the things that we're going to talk about throughout the quarter, it's true of. Again, not the kinetic K. This is the equilibrium K. Okay. There's one other little thing I want to add in, and this is as good a place as any, and that's because of the demographics of this class. A lot of you guys are very bio-oriented and very pharmacology type oriented of some sort. So if you're planning on doing any sort of medicine or things of that sort, this is a useful definition to know, even though not strictly a chemistry one. So we're going to just talk about the term real fast, and then we're going to use it to compare what we call binding efficiencies. Don't worry, you don't actually need to know any bio. If you know a bunch of bio, it'll help, or if you know a bunch of math, it'll help. So, if you're a bio major and you got your bio background, great. If you're an engineer and you got your strong math background, great. Either way, you're fine. Okay. So when we talk about a lot of drugs and a lot of other things too, this is a very biochemistry oriented things, we often talk about drugs and proteins binding because that's how a lot of drugs have an effect. So that's like a 2-minute version of like a 10-week class. If we were to write Kc for that, the Kc that we know and we've been talking about, when we've been dealing with, we would write products over reactants, right? So we have drug plus protein equals drug protein. Squished together because they're bound together. So we have our drug protein divided by our drug and our protein. That's no different than before. We could have filled in A, B, C. So Kc is related to the amount of drug needed to give a specific amount of the drug protein complex. And there's another thing that you can use here. And this is called the Kd. And they use this a lot when you're talking about drugs. And it's not really any different except that it's the reciprocal. So not being a doctor myself or being one of the founding doctors who decided to do this way, I'm not 100% sure why they decided to use Kd instead of Kc. Probably something about nicer numbers or something. But they'll use that. Notice it's not really any different though. Everything that you already know works. So it's just something I want to introduce here so that when you see it in a later class somewhere, you recognize it. Now, let's just use our incredible problem solving here to now answer a couple of questions here, okay? So you don't have to have a huge background on biology to do this. You just have to look at the numbers and know that KD is equal to 1 over KC. Let's do an example. So we have 2 drugs. We don't really care what they are. I've named them A and B. A has a much higher KD than drug B. So its KD is higher. If its KD is higher, what does that mean about its KC? It's lower, right? Because as one goes up, the other goes down. Okay. So drug A has a much higher KD than drug B. Both work on the same receptor, and both have similar cellular responses. In other words, they're basically the same drug, kind of, but just a tiny bit different. Answer the following questions. So again, you can just use math to do this. Which binds more tightly? So which has a higher affinity? Which one is going to stay more as a, let's reword this question. If I say it binds more tightly, are we going to have more product? Are we going to have more drug protein? Or are we going to have more reactants, more drug and protein? More products, right? Okay. So going back to this, if we have more products, what's going to happen to our KC? Goes up. So what happens to our KD? It goes down. So it's our low KD, or our drug B, right? Now, if you end up in one of these fields where you're talking about KD all the time, this would become second nature. But for now, we can use KC as a nice in-between. And we can say, so I'm going to talk through the exact same thing one more time. We can say that which binds more tightly, which means you're going to have a more product. You're going to have more drug protein complex. So when we look at our KC, we're going to have a higher KC, which means we're going to have a lower KD, which means it's drug B. Okay. So now getting into a little bit more, well, why would we care? If the binding is required for the drug to have an effect, which is pretty standard, you usually would want it to bind for that, what would you expect to be the more effective at lower doses? So which one has more things in the bound state? Drug A or drug B? Which, in other words, which one binds more tightly? It's not a trick question, it's up there. Drug B, right? We decided this one. We said, okay, this one binds more tightly, this one stays attached more, and if you need it to stay attached in order for it to work, which one's going to work best? Drug B, because it's attached more. Okay. So they can use this if they have 2 really, really, really similar drugs, which if you want to go into chemistry, drug development, that area of research, this becomes really important because you want to give people drugs at really low doses, because the lower the dose, the less likely it's going to go haywire and bind to a bunch of other things and, kill people. And generally when giving people drugs, you do not want to kill them. Key tip for you wannabe doctors out there. Okay. So quick review on this. In medical applications, a lot of times you use KD instead of KC when it comes to these drug. Maybe I should say pharmacological applications. So it's not really any different. When you hear about it in those classes, it's just 1 over KC. It's not any different than anything else except that it's the reciprocal. So the lower the KD, the higher the binding affinity, because the more it wants to stay in the bound state. And it could come in useful for a variety of different things in many of your lives. Okay. So now we're going to change gears a little bit. And we're going to see how we are able to find KCs of new reactions, and KPs, and theoretically Ka, Kbs, and KSPs, and Kfs, and whatever else, of a new reaction, a reaction that we don't know the number for. Maybe we can't calculate it for some reason. We can't go and do the experiment. For whatever reason, we don't know. But we have a bunch of reactions that we can add up to get the new reaction. So we're going to start by just seeing what happens, how can you manipulate the KCs by manipulating the reactions? And then we'll talk about adding them together. So let's take a kind of simple example. We'll keep with our N2O4 goes to 2NO example. And we know our Kc of that. We did that earlier. Now, write the equation for the Kc of the reverse reaction. So let's first start by writing the reverse reaction, yeah? So that's our reverse reaction. We just flipped it. Now what is our product? N2O4 is our product. So what goes on top? N2O4. And what goes on the bottom then? NO2, just NO2? Good. Okay, so we wrote our reverse reaction. We wrote our Kc. What do you notice about the two? Yeah, they're reciprocals of each other. They're inverses of each other. You just flip them. Which is really handy now that we know that, right? Because now every single time you want to do this, you just know, okay, if I know my value for Kc of the top one, if we know that Kc of the top one is a certain number, and we want to know the bottom one, what do? Just invert it. Do 1 over the answer, or 1 over Kc. So that'll be really handy. All right, next one. This one might seem a little less obvious about why we would want to do it, but do you remember back in 1B when you did Hess's law problems? Yeah, and you added up reactions and then you added up the delta H's. We're doing a similar sort of thing here, but the rules are different. And I stress that because a lot of people really like those problems, and these are similar, but the rules are different. So it's a slightly different game. So, and we can see why as we're going through this. So now let's do this one. What if we multiply the reaction by 2? So let's do that first. So we're back to our original example. And we multiply this by 2, and we multiply this by 2. What goes on our numerator now? NO4 to the 4th power. And what goes in our denominator now? N2O4 to the 2nd power. Okay. We're doing these long way just for kind of show you where it's coming from so you can remember it. But once we have these rules, we can just use them. Now that we have this, what's the difference between the two? The bottom one is just, is it multiplied by 2? No, it's squared, right? And we can extend that a little bit and say whatever we multiply it by, 2, 3, 4, 100, 15,000, it doesn't matter. You raise the Kc to that power, okay? So these are both really handy ways of manipulating equations. Okay? Just a quick review and making sure that we know that it's generic, that it works for generic things as well. We may have showed it for the N2O4 example, but it'll work for anything. If you reverse your equation, you just invert the equation, right? You just invert the equation, so you invert the Kc. And you don't have to do this every time now. You don't have to refigure this out. You just say, oh, if I want to reverse the equation, I invert the Kc. Done. And if you multiply the equation through by any number, remember you have to multiply the whole thing. Every single one has to be multiplied by that number. You just raise it to the power. Notice, not the same rules as Hess's law. I'm going to just stall for a minute. There's pens going everywhere, so I want to give you guys a second. Yeah?
Putting it to the power, since they're all the same, you need to factor out the power outside.
Yes and no. So in this case, for my generic case, I have them all the same. I didn't put in like A, B, C coefficients. And if they're all the same, so what he's asking is, let me repeat it for everyone. What he's asking is, since these are all the same, could we just put the power on the outside? Yes, if these are all the same. Now, if this was a 1 and a 2 and a 4, you could leave this as 4, 1, and 2, and then put the n on the outside. You know what I'm saying? In reality, how we're going to use these is actually we're going to have numbers. So what we can do is we can just take that whole number and raise it to whatever thing we multiplied through by, and we're all set.
So since you're multiplying with the same number, you just put it outside.
Yep. So if you know the KC already and you multiply through by 2, you just square the number. And if you have the number and you multiply through by 4, you raise it to the 4th power. Okay. So we're going to have motivational moments of the week for occasionally, especially because this is a long class. So I like this one. I came across it today and it made me happy. So you are living, you occupy space, and you have mass. So I just want to tell you all that you matter. I thought it was really cute. So I'll give you a second. I see people explaining it to their neighbors, so anyway. Group work, teaching each other, I like it. All right. Now let's take what we just did and expand it just a little bit. So now let's actually go through putting them together and using this to kind of manipulate things around. So we want to be able to look at different equations and see what we need to do with them to get to whatever equation we care about. And generally, I will tell you what equation you care about, because you need to know why you care about it. In real life, you would just care. Here, I need to tell you why. So we're going to use all the rules that we just did to do this. We're going to say, okay, well, if we flip this equation, we're going to invert the KC, because I'll give you the KCs. You'll have the KCs in front of you. Or if I need to multiply through by a number to make something cancel, and you need to raise that to the exponent, you'll have those KCs. And then you'll combine them together. So sticking with our really generic reaction, if two equations add to a new equation, you multiply the KCs. Okay? So if two equations add to a new equation, you multiply the KCs. So here I have AB goes to CD, but then my second equation is CD goes to EF. So now that you actually had kinetics, we can talk about something. We have something here. If this were a mechanism, right? It's not, but if it were a mechanism, what cancels? CD. So those go away, and we end up with AB goes to EF. So maybe this is 2 steps in a mechanism. Maybe it isn't. You can kind of do either. A lot of times they are. When we get to something called KF, we'll be doing that. We'll be saying we have 2 different reactions happening simultaneously and using Ks to find the new K. Now, if we want to find the Kc for this, we just multiply the 2 individual ones. Okay? So we take the Kc's, we multiply them together, and we get the new Kc. Notice, once again, not the same as Hess's law. What did you do in Hess's law? Just because, review is good. You added in Hess's law. Here you multiply. Okay, but what if we have a different situation? What if I don't give you this? What if I don't give you these nice equations that add right together and they equal the final one? Now we have to do a little bit of adjusting. So here we have something that's very, very similar. But let's look at the difference. Here we have AB goes to CD, and then we have EF goes to CD. If we add this up, we have AB, EF goes to 2 C's and 2 D's. It's not what we want. What do we have to do to get this equation? We have to flip the middle one. Okay, so let's do that. So we flip it. What happens to the Kc? Yep, to the -1 or 1 over, whichever you want to think of it as. When we multiply these together, we now multiply Kc over 1 over Kc double prime. And you would have numbers for these. At the moment, we're just keeping it generic, but eventually you would have numbers for them. All right. So let's do that. Let's do a few examples now with real numbers. As usual, I'm doing examples on the document camera. All right. We want to add to our bottom one in some form. If you want, draw a line here, it's up to you. And as we have it right now, this one's all set. That one's good. If we look at our two H's, that's all set too, so that's nice. If we look at this one, let's box it. That's all set, that follows down. And then if we look at these, they cancel. Do we have to do anything to this? No. This one was a nice one. They automatically add to equation 3, so we're just going to multiply the Kc's together. We add them together, or I'm sorry, we multiply them together. Or that was kind of nice. We didn't really have to do too much adjusting. We just got to say, let's go through, multiply, and we have our answer. The next one we have to do something to. When we look at this one, our C's are okay, our carbons are okay. Our CO2 is okay. So we're all set there. We're all set there. But we don't have any CO down here. We want the CO2, or excuse me, we want the CO to cancel. So we come over here. Does this cancel that out? Not quite, right? It doesn't quite cancel. What would we have to do to cancel it? You'd have to multiply by 2. Now, you usually will be okay if you just go ahead and do that, but let's double check the rest of them real fast. If we multiply this by 2, will it give us what we need here? Yeah. If we multiply this by 2, will it give us what we need there? Yeah. So let's just multiply everything by 2. And then that takes care of canceling this out, of bringing this down, and of bringing that down. If we multiply by 2, what happens to the Kc? Or in this case, Kp? Multiply by 2? Square it. Good. We square that. And now when we go to figure out our final answer, we say our final Kp, black, is equal to our first equation. We didn't do anything to, so we leave it alone. We don't touch that one. Our second one, we have squared to get our answer. Okay. Questions on that? No? just our quick recap. We reverse the reaction, you take the inverse of the Kc, and you can see that you can do it with the equation. That's not going to come up as much as just doing it with the number like we just did here. The examples that I did on the document camera are how you would be asked these questions. If you multiply the reaction by a number, you raise it to that exponent. It doesn't matter what it is. Just make sure you remember you raise it to that exponent. And then if you add the reactions to get a new reaction, you multiply the K's together. And this is really, really useful for the exact same reason that Hess's law was really, really useful. There are experiments that are very difficult to run in a controlled lab setting, and you still want the values for those. Those values are oftentimes still really useful for us. And if you can't measure it directly, but you can measure 2 or 3 other reactions and you can add them together to get that final reaction, now you have a value for a reaction that you need and you care about, even though you can't measure it directly. And that becomes really important because chemistry doesn't always do what we want it to do. A lot of research is trying to get around the fact that there are all these things in our way and all these problems that we can't quite do exactly what we want to do. And these are the types of ways that we can deal with that, just like we did with Hess's law. Okay. Now let's talk about something called the reaction quotient. And this is in many ways kind of the same thing as K. Not quite. K is at a very particular place. Q is everywhere. But other than that, it's very, very similar. So we'll define the reaction quotient. We'll say what's the difference between Q and K because they're going to look very similar. The equation for them is exactly the same. And we can use this value, once we talk about it, to decide which way a reaction is going to go. So far, everything that we've talked about in this course is talking about things at equilibrium. But things aren't always at equilibrium. At the very, very beginning of this chapter, we talked about that when we showed those graphs where we put a reactant in, and then we watch what happens. And depending on exactly what the reaction is doing, some of it goes away or we make more of it, something happens, it shifts. This is what Q allows us to do. It allows us to tell us which way it's going to shift. It's defined the same way as K. It's products over reactants raised to the stoichiometric coefficients. So the equation for it looks identical. If we have AB goes to C, it's C over A times B. That doesn't change. What the difference is the fact that K is only at equilibrium. It's a constant, it's a value for a given reaction at equilibrium. Q, on the other hand, is anywhere. Q is the conditions that it is at this moment in time. So it changes constantly. If you measure it at second 1, it changes again at second 2, and it'll change and change and change and change and change until it reaches equilibrium. And then Q is equal to K, and it just stays at K. Now, what this lets us do is it lets us tell which way the reaction is going to shift, because we know what K is equal to. So if we either are given Q or we calculate Q, we can compare it to K and say, what is that reaction going to do to reach equilibrium? Because if Q is not the same thing as K, it's not going to be at equilibrium. So if Q is less than K, the reaction is going to move forward. It's going to move in the right direction, the forward direction. Where if Q is greater than K, it's going to move in the reverse direction. Q is equal to K, we're already at equilibrium, it stays exactly where it is. That's the sort of short version. Now, it's good to be able to know things like this off the top of your head and be able to just kind of say it right back and use it and things of that sort. It's also good to understand why it is. And we can do this just by looking at the equations and looking at the numbers a little bit. So let's do that real quick. So I picked a generic reaction again. Generic reactions for this sort of thing are good. Notice Q defined the exact same way as K. They really are just different time points. K is at equilibrium, Q is everywhere else. If Q is less than K, okay, so K is equilibrium, K is what we're trying to get to. If Q is less than that, what does that mean about the amount of products? Is it too low or is it too high? It's too low, right? If Q is less than K, our number of products are too low. Now, if you want to make this number bigger, do you shift toward the reactants or away from them? Toward. So since your products are smaller, or if you want to think about it, your reactants are bigger than you want it, it's a combination of the two, it's got to shift to adjust. And so the reaction is going to move forward, right? This is just the reason behind why those rules work. They're rules because of this. Okay. So the exact reverse of this then. What if Q is greater than K? If Q is greater than K, do we have too many reactants or not enough? Q is greater than K. Well, now you have too many products, right? Now your numerator is too big if your Q is bigger than K. Or conversely, your reactants are too small, whichever. You need to adjust that. So if you want that number to be lower, if you want Q to equal K, and right now it's bigger than K, you want to lower that number, you need to lower the amount of the products. So which way are you going to shift, right or left? You want this number to be lower, so you need to shift away from it, so it's going to shift left. Now, if Q is equal to K, you're already at equilibrium, so you're done. You're just there. This becomes pretty handy when we start getting into situations where maybe instead of just adding reactant or just adding product, we've added all three. And before you can make your ICE table, you need to know whether you need to add some value or whether you need to subtract some value from each side. And you can't do that unless you know which way the reaction is going to move. And this is how you tell. Let's do an example. For the synthesis of ammonia at 375 degrees Celsius, I tell you the Kc. I give you the initial concentrations, and I ask you which way the reaction is going to shift. And going along with that, what's going to happen to the concentration of each gas when that happens? If we want to know which way a reaction shifts, step one is to find Q. And we can do that here just by filling these numbers in, because I didn't do anything too complicated with that. So we put our 0.48, we remember to square it because of our 2. We put our 0.76, we remember to cube it because of our 3. And we put our 0.6 down. And this gives us Q. Exact same way that we would find K, it's just that now we're not at equilibrium. Now we look at this, is 0.89 greater than or less than 1.2? Not a trick question. It's less than, yeah. So our Q is less than our K. We need that products to be larger to get this up to the value that K is, and so it's going to shift forward or shift to the right. All right. We'll just talk through the last part of the thing. What's going to happen to each reactant or each species? If we're shifting to the right, do we make more NH3 or less? More. If we're shifting to the right, do we make more N2 or less? Less. And if we're making, and what's going to happen to our H2? It's also going to be less. All right. Let's do another one. Ignore the little reactant thing right there. It's an animation out of order. All right. Kp for the reaction below is 5.6 times 10 to the 4th at 350 degrees Celsius. The initial pressures are, I give them to you, is the total pressure at the end less, greater, or the same? We have to think about this one a little bit more here. How many moles of reactants do we have here? 3. How many moles of product do we have? 2. So our pressure is going to change if that reaction shifts, right? If it shifts to the right, we're losing some moles of gas. If it shifts to the left, we're gaining some moles of gas. We need to figure out which way it's going to shift. Now, did I put any product in here? I have SO2 and I have O2. Did I put any product? No. If I don't have, if my concentration of one of my things, one of my species are 0, it's got to shift toward that, okay? So I don't have any product right now, so it's going to shift toward my products. Because right now my Q is 0, right? It's 0 over some numbers, it's 0. So it's got to shift forward. If it's shifting forward, we're going from 3 moles of gas to 2 moles of gas. And we can just use the stoichiometric coefficients to do this. Yeah, sure, we could actually calculate the exact number of moles, but all we care about right now is it going to go up or is it going to go down? So if we're combining 3 moles of gas and we're getting 2 moles of gas out of it, is our pressure overall, let's actually back up a little bit, is our moles overall going to go down or up? Our moles are going to go down. And if our moles go down, what happens to our pressure? It also goes down. So this is actually a Q question. It's just slightly in disguise. Because our Q is 0 right from the outset because there's no product. And then we actually look at our coefficients just to let us know, is our overall moles of gas going down or are our overall moles of gas going up? Because it's shifting forward, it's going down. If our moles go down, so do our pressure. And we're remembering, if you've forgotten about some of your stoichiometry and your ideal gas laws, it's in the beginning of your book, chapters 5, 8, and 11. And of course, office hours if you need help. Okay, so we have a reaction quotient now. We know that our reaction quotient is defined identically to K in terms of the equation, except they're at different time points. K is always at equilibrium. Q is anywhere. Maybe it's at equilibrium, maybe it's not. Maybe it's at the beginning, maybe it's in the middle. It's somewhere. So that's why your values are going to often differ. K is a constant for a given reaction at a particular temperature. If you change the temperature, it changes. If you change the reaction, it changes. Q is a different value at every point. So that's going to move around a lot. You can determine which way the reaction is going to shift by looking at Q and K. Because if Q is less than K, it's going to shift to the right. But if Q is greater than K, it's going to shift to the left. One moment here. We'll just fix that real fast. Sorry, I said the exact same thing on both sides. So let's repeat that. You can tell which way your reaction is going to shift based on your Q. So if your Q is less than K, it's going to shift to the right so that it can make more products. But if your Q is greater than K, it's going to shift to the left so you make less products. And if you're great at memorizing things, you can just kind of memorize those rules and use them. If you're not great at memorizing them, just think of it in terms of the products and whether the products are going up and down, and you can use that to help you out. Okay, so now our deep thought for the week. I thought this was going to be next time, but you get 2 of them in a day. Lucky you guys. If a king farts, is it a noble gas? People send me these things, and they're amazing. So, by the way, if you have a favorite, deep thought or motivational thought, you just go ahead and send it to me. Make my day and everybody else's if it's, warrants being shown here in class. Okay. Sorry, I'm a sucker for bad chemistry jokes. All right, calculating equilibrium constants. So we've kind of done this a little bit. Now it's time to get into this a little bit more in depth and get into some of the problem solving a little bit more in depth now that we have all of the component pieces. So far you've seen kind of level 1 versions of this, meaning, you know, you're given a lot of information, they're not kind of hiding information from you. Now we're gonna start doing more complicated ones. Someone made a pretty good observation in office hours the other day about what some of the problems that we did last time were, and it actually works pretty well for the whole class. That the difficulty in these topics actually isn't necessarily the chemistry. The difficulty in the topics is actually more of the problem solving and reading the questions very carefully, okay? If you're just trying to match numbers randomly, you're gonna have a hard time with it. You want to read it very carefully. Think about when you were prepping for the SAT, the problem solving parts of it. And there weren't set rules and set ways of doing everything. You kind of had to think about it. And this is going to be the same way. You want to be really careful about the reading part of it. For those of you who don't love chemistry, this is good news for you, because you don't have to get trapped up too much in the chemistry. That part isn't the rough part. Just focus on the problem solving aspects of it, and you'll be okay. And treat it like it's fun. It really is kind of like a game once you get the hang of it. It's just kind of playing around, filling in numbers. Have a little bit of fun with it. You don't get it right the first time, you get to crinkle up some pieces of paper and throw them and start over again. It's great. Okay, so we're gonna go back and forth a few different ways here. We're gonna figure out the equilibrium constants from the initial concentrations in Kc. We're gonna figure out Kc from experimental equilibrium calculations, which we've kind of already done. Make sure before you try any problems related to this section that you already know how to use Q to tell which way the reaction is going to shift. That tends to be mandatory for like 50% of these problems or so, and that you really have K down, that you know how to write K, that you know how to fill that into the reaction, because those are both going to come up in most of the problems in some way, shape, or form. Okay, this slide is mostly just for you guys to have. I'm not going to step through it in detail, I'm just going to do problems. But the sort of summary of this is that for most of these problems, you're going to have two main components. You're going to have an ice chart, which we've kind of shown you a simple one for, and you're going to have a Kc or Kp equation. This, by the way, goes for acids, bases, all the other Ks too. And now you're going to just fill into the ice chart and fill into the Kc equation with whatever you have, with whatever you know, with whatever the problem is given. A good tip to problem solving on these problems, if you get stuck, if you get to a point where you're like, now what do? I don't have an example problem to work off here. Look at the problem and say, what haven't I used yet? And a lot of times that'll help you out. So again, this is mostly for you. If you didn't get it copied, if you're trying to copy it from scratch, you probably didn't. Just pull it down from the website. This whole section is pretty much examples, because it's really the best way to figure out what's happening. For first one, calculate the number of moles of hydrogen that are present at equilibrium if the mixture of 0.3 moles of carbon monoxide, 0.3 moles of water is heated to 700 degrees Celsius, and I give you the Kc for it, in a 10-liter container. We have a few different pieces here that we're going to have to put together. Our first step when we do these sorts of things is generally go ahead and make our ice chart and see if we can fill in. The exception to that is if you're given all equilibrium values and you have everything that you need. This usually doesn't necessarily happen. The ice chart is a note-keeping device, is effectively what it amounts to. It's a way of making sure that you know what the problem is asking you and what information you have and what information you don't have. It's just a very organized way of doing it. So now we see what information do we have. So I added in a mixture of carbon monoxide and water. Did I put any hydrogen or carbon dioxide in that mixture to begin with? No. If I don't say that I added it, that means I didn't add any. So what's my initial amount of hydrogen? 0. And what's my initial amount of carbon dioxide? 0. Now, I give you case C, so you're probably going to want to deal in concentrations, since that's what I give you. When we get to water, in this case it's a gas because we're at 700 degrees Celsius, right? So in this case our water is a gas, not a liquid, so it gets included. I have 0.3 moles of water. Should I fill in 0.3 here? No. Good. Why? Is 0.3 a concentration? No. What do I have to do with 0.3? Divide it by the 10. Ice charts can get a little messy, and so a lot of times I won't worry about my sig figs until I start doing something. So I'm going to kind of keep that straight from the beginning. We'll worry about our sig figs at the end. For right now, I'm just going to put the numbers I have to in. My CO is going to be the exact same thing because I also added 0.3 moles of CO, so I have to divide that by 10 as well. Now we're kind of at a new point that we haven't run into yet, where we don't have any equilibrium values. What we did before is we had an equilibrium value, and so we could see how much that changed. Here I don't have that. So I'm going to instead put it in variable form because I have my Kc, and my Kc gives me some information. Which way is the reaction going to shift here, right or left? Is it going to shift toward the reactants or toward the products? The reactants, because there are no reactants, right? No reactants means it's got to shift toward the reactants. So I'm going to add some here. I don't know how much, but I'm going to add some. So I say plus X. Now, if I add XH2, how much CO2 do I add? I add X. What if there was there's not, but what if there was a coefficient of 2 here? How much would I have to add? 2X. Okay. So if I'm adding this much and this much, what's happening right here? Minus X and minus X. Awesome. So now we know our equilibrium in terms of variables. We have that. Again, we'll deal with sig figs later on. Now we fill into Kc. Because I only have one variable here, and I know my Kc equation. So if I only have one variable, and I know all my other numbers, I can figure out what X is, because what is our goal here but to find this value? Almost. Our goal is to use that value to find the moles of N. Okay. So we'll take Kc. And we'll fill into our K equation. To save on space, I'm not going to write out the equation itself, but now, some of the algebra on these problems can get a little bit nasty. A lot of times they turn into quadratic equations. So you need to be able to solve quadratic equations. We'll have some tricks that we'll teach you along the way to simplify them. In this case, though, we get to use a trick right away to simplify it. Because how else could I write this? I could just write it like this, right? Because those are the same thing. And I could just write this as x squared. And now I can just square root everything. And I can make my life a little bit simpler, okay? So I can square root the whole thing. That keeps it from being a quadratic. I wrote this question in a way that we could use that little trick. And I'm not going to do all the algebra out. I will trust that you can do it, and if you can't, you can come talk to me in office hours and I'll show you how you get it. What's my unit on that? We need to be a little bit careful that we get the right thing, right? What was my units on that? Was it moles? What was my unit here and here? Molarity. It may not be a bad idea in the ice charts because they're squished and you don't really want to have to write units on every number to just put the unit that you're using somewhere outside, whether that be atmospheres, moles, or molarity. Yeah? Oh, thank you. Yes, right here. There should be a 0 in here. Thank you. Okay, so is this the value that we want? Now, the big key to making sure you get questions right a lot of times, if you kind of already know what you're doing, is making sure, did you actually answer the question? What are we actually trying to figure out? Moles of H2. So what do we have to do with this number? This is moles per liter, so we just need to multiply by 10 liters. Because they didn't say that our container changed volume, and we get our final value. Okay. Now, in this case, we knew all our initial values, and we knew our KC. And so we had to use variables. Sometimes that'll move around a little bit. You've already seen examples of what happens if we know our initial and our final values, and we need to find KC off that. We did that a while ago. So we'll just kind of, all versions of this is free game, right? Let's do another one. So here we have this equation. Hydrogen plus iodine goes to 2HI. I give you the Kc for it. At this temperature, we have 0.3 moles of hydrogen and 0.3 moles of iodine in a 1 liter container to react. What concentration of HI is present at equilibrium? We're going to do basically the same thing. And by basically, I mean we're going to do the same thing. So this is a good time to play beat me to the answer. We're going to do basically the exact same thing as the above one. So I'm going to keep going at the exact same pace for the people who need it. The people who don't, try to get the answer faster than I do. When we start off, I tell you how much hydrogen and how much iodine we put. Now this time it's in a 1 liter container. So we are technically dividing by the volume. It's just that doesn't actually change anything. How much HI do I have initially? Did I add any in? I don't ever add any in, so it's 0. We can add a little note about our units if we want. Now, we don't know any of our equilibrium values. So our changes, we're not going to know what they are. So over here we're going to do minus x because it's got to shift to the right because of that 0. And now we have our equilibrium values in terms. Oh, thank you guys. So we have our 1 here, our 2 here, so this should definitely be 2x. Now, this is going to be 0 plus 2x, so we just write our 2x. Okay, now we fill into our K equation. So there's 2 very, very common errors that happen in this sort of problem. The first one, we just saw, for getting the 2x. The second one comes in when we actually fill into the K equation, and it's a very similar issue. When we fill into the Kc equation, and we fill in our products here, what goes inside? Do we just do x here, or do we do 2x? Are we done with that numerator? What else do we have to do? Square it. So when it goes into the numerator, you have that 2x and you have it squared. And a lot of times one or both gets forgotten about. In our bottom, we're going to have that, because it's H2, and we're going to multiply it by the exact same thing again for I2. So I'm just going to save a little bit of time this time and make it squared. But we know it's squared here because I'm multiplying this by that. And since I'm multiplying this by that, and they happen to be the same thing, it's squared. Again, I'm doing that on purpose to make the algebra here a little bit simpler for us. So if I want to solve for x, the easiest way is to just square root the entire equation, because that simplifies our math down so we don't have a quadratic. Because quadratic equations aren't really the most fun thing in the world to do. And now we're back to something that we have to rearrange it a bunch, but nothing particularly terrible, right? So pick your favorite way of doing algebra rearrangement. And if you're having problems with that, just come talk to me and I'll help you out. We have our 0.235 molar. Everything we did was 3 sig figs, so it's 3 sig figs. Now let's see what we're looking for here. What concentration of HI is present at equilibrium? Is that our concentration of HI? No. What is this our concentration of? I didn't ask, but what is this our concentration of? Is it our concentration of anything? Is it our concentration of H2 and I2? No. This is not a concentration that we can do anything with. Okay. If I had asked you for H2 and I2, what would you have to do? 0.300 minus 0.235. In my case, or in our case, I asked you for HI, so what do you have to do? Yep, you need 2x. And so we get that. In all of these cases, just for kind of the sake of moving along in examples, I don't ask you to calculate everything you could. It's not a bad idea to go back through in your free time and calculate the rest of them, right? In this top one, I could have asked you for all the concentrations. In this bottom one, I could have asked you for all the concentrations. Okay, next one. Like I said, our best way of doing these are just tons and tons and tons of examples. I'll leave this up here a little bit so you have it if you need it. Okay, now I do something a little bit different with how I give you the equation. Mainly, do I give you the equation? No, not quite. What do I do instead? I tell you about it. We have the decomposition of phosphorus pentachloride. So what is phosphorus pentachloride? We have PCl5. And it's decomposing into phosphorus trichloride. and chlorine gas. Again, remember, you need to know your nomenclature because I can always write things like this. So go back, review it if you need it, ask for help if you need it. I tell you the Kc, which means that we're going to be dealing in concentrations. If I told you the Kp, then you would want to deal in atmospheres. And I say find the concentrations of each, and then I ask for something else too. I ask for the percent decomposition. So we're going to have to kind of work through what that means once we get there. But that's really sort of an add-on, so let's do the rest of it first. And we make our ice chart. Again, it's our note-keeping device. There's two sort of easy initial ones to fill in. What are those? How much product do I have? 0. So let's get that out of the way first. We get that out of the way. Now PCl5. Do I fill in one? Okay, just some extra time for you guys to fill in notes there. Do I fill in 1 gram? No, right? That's not a concentration. So what do I have to do with that 1 gram first? Turn it into moles, good. I also can't just divide it by 250, right? Several things wrong with that. 1, that's not liters, and 2, that's not a concentration unit in terms of what we need for Kc. So I need to take the 1 gram, and I need to go to my periodic table, and I need to find my molecular mass. Now, what am I looking for my molecular mass of? Phosphorus, pentachloride, trichloride, or chlorine? The pentachloride, right? Because that's the thing that I know that I have that much grams of phosphorus pentachloride. So that's the molar mass that I need. Okay. So we can fill that in. Now, am I going to divide that by 250? Not 250, why? That's in mils, so what do I need to divide it by? And I'm going to do it all in one step, because you guys are in 1C. You've been doing a lot of these. If you need to break it down into more steps, you need to break it down into more steps. Not a big deal, just do it. I'd say that there's no wrong way to do chemistry, but there's definitely a lot of wrong ways to do chemistry, but there are also several right ways, so however you need. So 0.019208, that's what we fill in, because that's our molarity. And now we can do pretty much the same thing that we have been doing. We know that it's going to go to the right. All the cases that we've had so far in this little section, we've had Q either equal to 0 or infinity. We've had some side that had 0. That won't always be true, so keep that in mind. Sometimes you may actually have to calculate Q to decide which side gets the plus and which side gets the minus. But other than that, it's the same thing. When you get to here, it's a good time to double check and make sure that your coefficients didn't make effect that you forgot about. We're fine because they're all 1. And now we fill into our K equation. So I'm going to go ahead and put this as step 1. This is step 2. This is step 3 in case you're like, you go back to your notes and you're not sure what was happening there. So we fill into our Kc. Can we just take the square root of that? No, because the bottom's not squared this time. What do we have to do here? we have to do a quadratic equation. There's not really any way around it. So, mildly annoyed face quadratic. I pretty much always get asked this. So are you allowed to use graphing calculators on the exam? No. What can you use though? Scientific calculators. Can scientific calculators solve quadratics? They can. They're all a little bit different, and I absolutely don't promise that I know how. I can play around with your particular calculator and see, but there are ways to do it. Are you allowed to do that on the exam? Show of hands, who wants to use it on the exam? Okay, sure, we'll do that on the exam. Yeah, use technology. If you have technology, use it. The only reason we don't let you use graphing calculators is because we're afraid of cheating. It's not because we're afraid of the technology. So you're more than welcome to do it. Okay, so that's multiplied up and subtracted over so that it's in the right form for the quadratic equation. You get that? So quadratic, so you get two answers. Which one do you pick? You pick the one that makes sense. One of them is going to make sense. One of them is going to be a negative, or it's going to be really high, or there's going to be one value that makes a lot of sense. There's going to be one value that doesn't. Pick the one that makes sense. Now, we come up here and figure out what I wanted. Final concentrations of each species. So this time, we need to figure them all out. But we have two of them already, right? What is x equal to? What is x equal to? Yeah, in this case, x is actually useful. Well, okay, it was useful in the other ones too. But in this case, it's an actual concentration that we need. Two of them. So we have those two. How do we figure out PCl5? We subtract. So that takes care of each of the species that we need. There's one last step that we are going, no, we have time, it's fast. Percent decomposition. So it's a percent, right? And it's how much is decomposed. So it's just amount decomposed over total. So in this case, in variable form, how much decomposed? How much went away? And how much did we initially have? And it's a percent, so we multiply it by 100. So we've never talked about percent decomposition, but we know what percentages mean. We know what decomposition means. We can figure it out. We fill those values in. And we get our percent decomposition. And we're done. We'll finish up this section next time. We just have, I think, one or two more examples to do.